Welcome, everyone. Today we're going to have Javier Redondo, Professor Javier Redondo from the University of Zaragoza. So before I introduce him, I'll just simply remind the rules, which today are going to be slightly different. Javier is okay with being interrupted by urgent questions, in which case you are free to just type your question in the Zoom chat or in the chat of the YouTube channel. And in other ways, in other case, we may always have you can always ask at the end of the session during the last 10-15 minutes of the session of today's seminar. So without more, let me just introduce Javier Redondo. Javier Redondo did his undergrad in physics at the University of Zaragoza, and then he went to Barcelona, where he did his PhD at IFAE, Instituto de Física de Altas Energías, if I understand correctly, on axion-like particles, right? And then he was a postdoc in Hamburg, in Decay, in the Max Planck Physik in Feynman, Munich, where we met. And then after a few years, he got a Ramón y Cajal Fellowship in Zaragoza. And since 2020, he's a professor contratado doctor in Zaragoza, right? Although he also holds his affiliation to the Max Planck Physik in Munich as Mercator Fellow. So indeed, Javi, it's great having you here. You know that, so this is an Astrophysics Institute, and you're aware that we will rather have like a big introductory section on the topic of axions, just because most of the audience is not so used to it. But I'm sure you will do a very, very great job. So thanks again for coming, and all yours. Okay.
Thanks, Carlos, very much for this lovely introduction. So I'm very happy to be here online, although I could be much happier was I in the Canary Islands with you all, particularly in this very benign time of the year. But I proposed myself I will try not to be comprehensive, so that actually you are forced to invite me to give another seminar. And if I'm lucky and the pandemic is already gone, then I will be able to just stop by and give the talk in person. So the title of my talk is the quest for axions, and in this talk I just wanted to introduce you to the axion, and which is motivated by the strong CP problem. So I will tell you a little bit about this problem. I will tell you about axions, and then I will tell you about how do we search for axions. What do we know about the axions from actually from the stars, and then how axions are dark matter, in which way they are dark matter, and how can we find them in some dark matter experiments. So I've tried to tune a little bit my talk, so it's a little bit tuned to the astrophysicist. So I try to highlight some topics, and some others I will just completely ignore. I'm very sorry if your favorite topic is ignored, but as I told you, this is a very nice excuse for you to invite me again. So let's go and start with it. So my talk starts very broad, but just reminding you that parity and time reversal, so these are transformations in physics, and we know that everyday life physics is just not invariant under these transformations. So actually, everyday life physics is not invariant under parity and time reversal. This we know, everyone that has a mirror at home knows this very well, and everybody who is a little bit older than 18 years old knows that time reversal is a pain in the buttocks. But funnily enough, this that is completely obvious for macroscopical systems. It is also true for microscopical systems, actually for the smallest systems or the smallest freaks of nature that we can play with, which are the elementary particles. Already from the 60s, we know that the electroweak interactions violate parity from these beautiful experiments of Wood et al. Of the decay of cobalt that show that the amount of times that the electron goes in the direction of in the anti-direction of the spin is different from the amount of times that the electron goes in the direction of the spin. And so life is different at both sides of a mirror, as you can see here. And it was much later, already in the 90s, since it was experimentally proved that actually the time reversal or time reversal is a symmetry which is or a transformation which is irrelevant for nature because it's violated by electroweak interactions, in particular in the decays of neutral kaons, which are asymmetrical between the antiparticle and particle. So, well, this is this is the case in the electroweak interactions, but funnily enough, this is not the case in the strong interactions. Okay, the strong nuclear force seems to be parity and time reversal conserving completely, right? And this is very interesting, and this is very funny, very particular. And this is because the theory that is used to describe the strong interactions, which is called quantum chromodynamics, is a quantum field theory of quarks and gluons. Here you have the Lagrangian density. It's not very relevant that you know all the pieces here, but yeah, the Lagrangian density depends on the gluon fields G and the quark fields Q. And it has two interesting pieces in general. Any Lagrangian of quantum chromodynamics with these particularities, it has a piece that is parity and time reversal conserving, and this can be shown. But it has another piece which it has to be there in a gauge theory, and a non-abelian gauge theory. Non-abelian is it's very important because the gluons are self-interacting, and so in order for having a confining force, you rely on the gluonic forces at large distances, and this required the theory to be non-abelian, and this non-abelian theory is required this part here, which violates explicitly parity and time reversal, and this part involves the gluonic fields here in capital G, and the fine structure constant of the strong interactions, alpha strong, and then one parameter theta, okay? And this parameter theta is an angle, and so as long as it is not zero, this term here will induce observables, will induce parity and time reversal observables, which are proportional to the value of this theta, which is a parameter, right? And this theta, it has to be measured in nature, and the meaning that it has in the theory is that it is an angle that allows to define from 0 to 2 pi, that defines essentially a gauge field, a gauge invariant vacuum, gluonic vacuum, something like this, the vacuum energy. So you choose your value of theta, and then you have your theory of quantum chromodynamics. But as long as you don't choose theta equals 0, it's going to be going to violate parity and time reversal. In particular, the most famous parity and time reversal observable that has been trying to search for is the electric dipole moment of the neutron. So imagine that a neutron is just a ball of quarks bound together by gluons, and we know that neutrons have a magnetic moment, and in principle they could have a dipole moment thanks to this theta parameter. And actually one can estimate that the value of the electric dipole moment would be of something like 10 to the minus 15 times the charge of the electron centimeter multiplied by theta. Okay, this is more or less the size of the neutron times the electric charge of the quarks multiplied by theta. So if theta is over 1, you would have an electron times femtometer or so, which is the typical size of a neutron. And actually, if one would have actually a dipole moment, in addition to the magnetic moment that we know already the neutrons have, you can see immediately that if you perform a parity transformation, which is just reversing, which is reversing here, then you think that the dipole moment, the magnetic dipole moment, is produced by electric current. This current is not reversed, or is twice reversed, so it stays in the same place. So the dipole moment will stay in the same direction. But if the dipole moment is produced by a separation of charges from the quarks, then if you just do a parity transformation, this is only one direction, so it will change sign. And you see that making a parity transformation does not leave the neutron invariant. So in principle, in nature, we would have these two states of neutrons, and this can be used to search for oscillations between these two states of a neutron. And this has been used to search for neutron EDMs already since the 50s. And already since the 50s, the search has been fruitless. Already the first limit put a very strong constraint on theta, but as technical improvements have progressed, so the upper limit on the electric dipole moment of the neutron has been decreasing and decreasing until today is of the order of 10 to the minus 26 electron charges times centimeter. So far, the bottom line is that the electric dipole moment of the neutron is not observed. And the same happens with electric dipole moments of all hadrons, of other strongly interacting bounded particles. And that's why we think that strong interactions have no CP violation, or parity and time reversal violation. So if we have a diagram, it's somehow funny that among all the possible values that theta could have taken in nature, the actual theory, or the actual theory of the strong interactions that we have to use is precisely theta equals 0, and actually the experimental limit is something like 10 to the minus 10. Okay, so theta has to be 10 to the minus 10. So this is called the so-called strong CP problem. Is theta so small, so ridiculously small, and so why neutrons and anti-neutrons essentially behave in the same way in nature? Why, in principle, according to our knowledge of gauge theories, it would have been very natural to have theta different from 0. Okay, so this is actually not a problem, but it actually can be a hint that something is at work there, making this theta parameter very small. And this was the attitude that was taken by Roberto Pache and Helen Quinn in the 80s. In 77, they put out this paper in which they came with a very simple idea in a very complicated way. So I'm going to explain you the very simple idea. So what they found, and I find completely illuminating, is that actually the vacuum energy of QCD depends on theta. So this now graph shows you the energy density of the different theta vacuums that you can choose for QCD. Okay, so it turns out that this energy is minimal for theta equals 0. Okay, and this is a key observation, because now if you think that you can promote the standard model of particle physics, or your QCD, in such a way that theta is not a constant of your theory, but it becomes a dynamical field, then you will have automatically that the field, given enough time, it will relax its vacuum expectation value to be theta equals 0, because it's the minimum energy configuration, okay, as long as you have some dissipation. So then, yes, so let's say the idea of Pache and Quinn is extremely simple. It's just use the fact that QCD favors theta equals 0 energetically by just promoting theta to a dynamical field. And then QCD will set theta to 0 in the vacuum. So this could explain perfectly why theta is observed to be so small in the universe, or in the lab today. Very nice. But aren't we forgetting something with this definition? Yeah, indeed, the theory of Pache and Quinn has a very important implication that escaped to them, and it is that once you have a field and you can expand it around the minimum of its potential, and the field excitations around minimum, they lead to what's called, they lead to particles. They can be quantized, and they have the same characteristic than particles with mass, okay? And this was not realized by Pache and Quinn in this paper, but immediately, I think a few weeks later, Steven Weinberg, or a few months later, Weinberg and Wilczek, both Nobel Prizes like Higgs, they pointed out that there will be a new particle as a consequence of the theory of Pache-Quinn. And Steven Weinberg, so the theory of Pache-Quinn involved some Higgs fields. So he called the new particle a Higgset. Okay, so this was the original name, but Wilczek, which was more humorous, he realized, or he pointed out, that he clears the strong CP problem with an axial symmetry, like he is, and he was reminded of this cleaning by his favorite soap, or a very famous detergent in the US. So he decided to call the particle the Axion because of its relation to the axial symmetry. And of course, the funny name got stuck, and Higgs-led was never forgotten. So just as a technical note, when you want to make an angle dynamical, the minimal theory that the minimal Lagrangian that you want to write, it includes the theta angle that I've already told you that has to be there, but you have to provide a kinetic term for theta. So now we would need to write this, but a Lagrangian density has to have energy dimensions equal to 4, and because angles have no energy dimensions, this piece has only energy dimension 2. So this has to be combined. It has to be any theory that produces a dynamical theta is going to need the existence of a new energy scale, which is called Fa here, which is called the Axion decay constant. Okay, and normally one defines now theta as the Axion field finally divided by this energy scale. Okay, so the Axion field has dimensions and theta has not, because it's divided by this energy scale. So the existence of the Axion is going to point us to a new energy scale, a new fundamental scale in nature. This is extremely important. And this is extremely important for you to remember that theta is the Axion field divided by this energy scale, because the way the Axion in principle communicates with the rest of the standard model and is going to interact as a particle is going to depend crucially on this property. And here you have exactly why. So you see that now the Axion field interacts with gluons, or through gluons, and since gluons interact with the rest of the particles, the standard model, either directly or indirectly, now the Axion is going to have interactions with the rest of the particles of the standard model that we can predict. Okay. In particular, by the way, the Axion has the same quantum numbers than the eta prime, a particle of the standard model, a meson of the standard model, and it's going to mix quantum mechanically with the eta prime. But the important thing for you to catch up is that every time, so all the couplings, all this connection between axions and gluons is suppressed by this energy scale. So if this energy scale is very large, this connection is going to be very weak. And actually, this is a very important thing to know about axions, that due to this coupling of the axion to gluons, so the axions coupled to they suffer the QCD potential. So the axion mass, which is nothing by the second derivative of the potential at the minimum, is inversely proportional to Fa, of course. But also the couplings to hadrons and photons, which the axion inherits from the mixing with eta prime. The axion becomes a kind of a meson, but whose properties are always suppressed by 1 over Fa with respect to the mesons of the standard model. So the important thing to remember from this slide is that the axion has a mass and couplings in such a way that the lighter it is, the smaller its mass, the more weakly interacting is going to be. Okay. So very good. So now that we know a little bit about the axion and the most important characteristics, we can just write down a phenomenological parameter space, which is going to be depending on this axion decay constant, or the axion mass, which is proportional to it, as I have written down here. And this proportionality constant is given by low energy QCD, the pi and mass and so on. But this is not very relevant. But the important thing is that these two things are linked for the QCD axion. Now, if the axion decay constant is not very large, then axions are like mesons, and they have been tried to find in experiments, in laboratory experiments, colliders, beam dumps, and so on. So typical particle physics experiments. And but they have not been found. So this region was very fastly excluded. And then we started, or people proposed immediately, that the only viable axion models had to be invisible, because the new energy new energy scale has to be much larger than the electroweak scale of 200 GeV. And these axions are so weakly interacting that were called invisible models, but they were soon found actually not to be invisible. So at the beginning, we called them invisible because we thought that there would not be any chance that we can find these axions, but still they can solve the strong CP problem. So it was a kind of string theory for the quantum gravity. So yeah, we can have quantum gravity, but unfortunately, we will never be able to measure anything related to fundamental strings. However, this was very soon discovered to be not to be the case. And this is when people realized that even a very weakly interacting particle, if its mass is small enough, can have a big impact in astrophysics, in stellar evolution, right? And so the idea here is it's very simple and probably very well known to all of you. The idea is that if you emit a weakly interacting particle, or if you have a weakly interacting particle that can be produced in interactions with a stellar plasma, and this particle is very weak, like neutrinos, for instance, so can be produced very rarely in the interiors of stars. But once once they are produced, they escape immediately. So they drain energy very efficiently. Oh, they can be, oh, sorry, since and this takes some energy from the core of the stars. But now this energy has to compete with the typical energy losses of stars, which come from photons from the surface or neutrinos from the interior, right? So because photons from the surface is a surface effect, and the photon opacity is relatively small, axions can be extremely efficient, just like neutrinos can be extremely efficient in cooling stars, and therefore they can compete with neutrinos and photons. So the basic idea is that one has, so we have studied many stellar systems, trying to find systems that cool very efficiently, and the idea is that, or what we have found is that typically too much cooling is very strongly excluded. Okay, so one can always put a very strong constraint on the couplings of axions to the plasma particles. But sometimes, and this is very interesting, sometimes some systems improve the matching of observations with theory versus observations if we add some additional axion cooling. Okay, and these systems are typically, are actually four systems: the tip of the red giant branch, the white dwarf luminosity function, the ratio of horizontal branch stars to a red giant branch in globular clusters, and the cooling of the neutron star in Cassiopeia A. So these ones, so this is the visual summary of what I've told you. So you can, in this diagram, you can put in this blue and gray colors, you can put very strong constraints. So axions in these regions would just have a very strong impact on stars, such a strong impact that we don't observe it. But in these red regions, it could happen that they improve the observations with theory. So axions could actually be already showing up as additional cooling in stellar systems. And you see the relevant energy scale would be 10 to the 9 GeV, so 1 billion GeV, so something like 1 million times higher than the electroweak scale. And this corresponds to a 10 milli-electron volt mass for the axion, very close to the neutrinos. Very good. So this is excluded, and this is some astro hints. So what can we do about it? Well, funnily enough, so there's a very clear thing that we can do about it, and it's try to, so if axions are being produced from stars, they will be produced by a sun, and we can actually try to go and search for these axions. So, and the sun is a very well-known star, and this allows us to predict what is the flux of axions that would come from the sun. And it falls into two categories, because axions couple to photons, just like neutral pions and other mesons. So one can have the same Primakov effect to produce axions. So you can produce an axion with when one of the photons of the interior of the sun interacts with the electric field of an electron or an ion, and then producing the axion through this axion coupling. And this axion to photon coupling is generic for axions, so it's always there, although it can be sometimes accidentally very small, but it's not typical. So typically this thing is always there. And one can have from these hadronic axions that are called, one has a prediction for the spectrum of axions after integrating over a solar model, which picks around 3 kilo electron volts of energy. And this is because in this transition, photon gives all the energy to the axion, and photons in the interior of the sun, in the center, have kilo electron volt energies. Okay. But in some of the theories, the axion couples to electrons. So this is not. The coupling of axions to electrons is not guaranteed, but in some theories can be quite large. These axions are called non-hadronic or non. Yeah, because they not only have hadronic interactions, and with these couplings, axions can be emitted more efficiently in the excitations of nuclei or recombinations of electrons into nuclei, into bound states of electrons, or just axions radiated by Bremsstrahlung, or just producing Compton scattering of photons. So in this case, one has the prediction is here, let's say, is this total flux, and it has more features, which is very interesting. So it has the features of the typical bound transitions and edges from recombination. Okay, and it can be quite more intense and peak around 1 kilo electron volt as well. So, and this, of course, these fluxes are proportional to the couplings, which are not known at the moment. And these are the things that we want to compute, okay? But here you have the typical fluxes for the typical values for milli electron volt mass axions. So we are talking about something like 10 to the 20 axions, solar axions per kilo electron volt per year per square meter, okay? 10 to the 20 per kilo electron volt per year per square meter at axions at the position of the Earth from the sun. So this is a relatively large number. How can we detect it? The most promising idea is the so-called Helioscope proposed by Sikivi in '83. The idea is very simple. So because axions couple to photons, if you have an axion that comes here and you put a very strong magnetic field, so the inverse Primakov effect can happen, and the axion can absorb 1 photon of the magnetic field and convert into a photon. And the nice thing is that this conversion can happen coherently along the whole trajectory of the axion inside of the magnetic field. Okay, so this conversion probability you can see it as an oscillation between axions in photons in a background magnetic field, just completely analogous to neutrino oscillations. Okay. And so you see here that there's this function. So the conversion probability, it depends on the length, but sinusoidally on the axion mass, the length of the magnet, and the energy of the photon. So if this quantity is such that that the argument is small, then we are in the coherent limit where the sign is the argument, and the probability becomes multiplied by L squared. So you see here, and you see that actually you are having a coherent conversion across the whole magnet. And this can be quite powerful. This can boost very nicely the conversion probability. And this can give us, with a magnetic field of 3 Tesla or so, and a length of 20 meters, this can give us the typical conversion probability of 10 to the minus 20 to convert, to get something like 1 photon, or 1 reconverted photon per kilo electron volt per year and per meter that we need perhaps to discover the axion. The idea is that these X-rays would be then focused, or can be then focused by X-ray optics, and then detected by extremely low background detectors, because we are expecting something like 1 event per year, or something like this. Okay, so these slow background techniques have to be at play here to detect very small numbers. So these experiments have already been done to a certain scale with in the CAST experiment. But now we are progressing because the strongest experiment to date was using a dipole moment from the CERN accelerator, from the CERN ring. And this was a very strong magnet, 9 Tesla. But the aperture was very small. So therefore you cannot have very many axions entering into your experiment. But you see here, the experiment is very nice. They took one of these giant magnets, they put it on a crane that was able to point at the sun for 2 hours per day, and put detectors and X-ray optics to maximize the signal to noise. And they had very interesting results, almost as strong as the astrophysical limits, as I will show you now. But it was not enough to surpass the astrophysical limits. But now, after this experiment has been a success, there's a strong community, in particular in Zaragoza here, that is involved in building the so-called International Axion Observatory, which would be the ultimate experiment that we can do to search for solar axions. And this would be of a much higher size with a dedicated magnet, with which one can track something like 12 hours a day, 8 bores of 6 centimeter diameter, so a few square meters of aperture to detect many axions, and dedicated X-ray optics and low background detectors, different detectors. So this is still a dream, but actually baby JAXA, which is an intermediate step, is being actively pursued at this moment, and it will take place hopefully at this in the next few years. And yeah, progress is being made in this intermediate step. And here, this is a plot in which I wanted to show you just simply in the plane of axion mass versus coupling to photons, which is a very typical representation of the parameter space of axions, where, since I talked, well, you can see several things, that the axion coupling is proportional to the axion mass for QCD axions, as I told you, so that QCD axion models are typically in this yellow band. So this is the theory prediction. While other axion-like particles, different type of other particles that can have couplings to 2 photons can be in any place of this diagram. But typical axions are here. And these are the astrophysical limits, the very strong astrophysical limits, horizontal branch stars. And these are the limits of the last helioscope cast that I told you before. So they will exclude this region. But going to baby JAXA or JAXA configurations, so much larger volumes, etc., one can really search for axions in this parameter space, which is extremely interesting. This even in the case of hadronic axions, but for non-hadronic axions, one can actually even be not only discover axions, but also be sensitive to the regions where they could explain the astrophysical anomalies that I told you before. Which are these regions here, which happen to be different for different axion models, unfortunately. But in principle, some models will be can be detected with JAXA. And I think this is very exciting because yeah, JAXA would be able to tell us something, or might be able to tell us something about axions in the milli-electron volt frontier. Very good. So before I switch to dark matter, I just wanted to tell you that this the fact that or very similar phenomenon to the one that is exploited in Axion helioscopes is or might be at work in the propagation of photons across the universe. And the idea is very simple. The universe is filled with magnetic fields, as you know very well. So we have photons that propagate in these magnetic fields. At any point, they can convert into an axion. Okay, and we have seen already that this probability, the conversion probability, can be coherent, so it can be large, and these magnetic fields in the universe can have large coherence lengths. But it also has some features, like, for instance, it is energy dependent, right? And it's oscillatory in some ranges, right? So one can have, one can try to discover axion-like particles, but by just looking for oscillations in the spectra of distant sources, and so on. Moreover, so it is only one of the 2 polarizations of photons that can convert into an axion-like particle in a given magnetic field, because the interaction is electric times magnetic. the interaction of axion-like particles. So you can have also polarization effects. Polarization can be created, so this can also be exploited. And this has led to very interesting bounds and even some hints, as I'll tell you before. But they typically rely, and this is the weak point here, they typically rely on not very well known magnetic fields in the universe, right? So we typically know some sizes and some constraints on the coherent lengths, but we don't know magnetic fields along the line of our two sources so well. So, but perhaps the most interesting, along these lines, the most interesting hint that has been pointed out in the last already decade is the transparency of the universe to 10 electron volt gammas, to very high energy gamma rays. And here the effect is very simple. Imagine that you have a region of the universe which is very opaque, just perhaps because it is, well, sorry, just imagine that you have, not a region of the universe, you can have a very high energy cosmic gamma rays, which will have a large opacity because of pair production in against the CMB or the infrared photon background. So you have photons that typically, if you go very far away, they will not be able to reach the Earth, just simply because they will be absorbed in one of these natural processes. But if now they can be converted into axion-like particles close to the source, and then reconverted close to us in a different magnetic field, then you could have a decreased opacity just through the effect of this axion-like particle. And this has been, in several analyses, this was observed. Here you have these two references, although in some other analysis and with other perspectives, these hints that the universe could be anomalously transparent, they are gone. They are not there. Okay, and this would point out to axion-like particles in this area here. However, as you see, there are other constraints that can more or less kill this hypothesis, like this constraint that I told you, like, for instance, done with Fermi-Lat of the observation of this source, and other things and other observations that can help could be a very interesting observation, very interesting combined effects, a combination of the things that I've told you previously. For instance, imagine that you have a supernova explosion and some axions are produced in the supernova explosion. Now they can travel, these axions, they travel towards us, and they encounter magnetic fields in our direction, and then they can be converted to photons. But these photons will have the same energy than the axions that come from the interior of the supernova, which can be as high as 100 mega electron volts. So they could be very hot X-rays. Well, not X. They are gamma rays, right? With these energies. So if you point to your telescope or if you don't detect these gamma rays coinciding with the explosion of a supernova, then you can just constrain the existence of axions very strongly, and this could be a possibility of exploring this region here. Okay, this was something. These are some phenomena I wanted to tell you because they can be of interest for astrophysicists. You can ask me about them more later. So let me just go to dark matters then. So the first thing we have to learn is that action dark matter is to some extent completely unavoidable. And this is a very strong point towards actions of dark matter candidates. So if you had told me that the action exists to solve the strong CP problem or to explain this strong CP problem, I would have, after some time, I would have realized that the action would produce dark matter, and there has to be some dark matter in the universe. I would have predicted dark matter based on the action as well. But the history was not like that, of course. We knew a little bit more about dark matter before. Well, perhaps it was a little bit like this. Okay, but okay, let me just go to the physics. So the idea is very simple. the idea is that if theta is a dynamical field and is going to relax to its minimum, if this field has very low friction, okay, which is what happens when the axion is very weakly interacting, so then it's going to go to the minimum like a damped harmonic oscillator, where the damping comes from the expansion of the universe, and that's it. And this gives you this particular behavior. So the axion goes towards zero, overshoots, and then comes back and oscillates around the minimum with a damped amplitude. So that the prediction is that today, because the universe has a finite lifetime, the axion field, or theta, would be oscillating in time. And the frequency of these oscillations can be calculated, well, can be identified to the second derivative of this potential, which is essentially the axion mass. So the prediction is axions are, so the axion field, the theta field, is oscillating today with some amplitude at the frequency of the given by the axion mass. And these coherent oscillations, they behave essentially like a gas of, well, without pressure, okay? And this pressureless gas is essentially cosmological dark matter. And yeah, one can relate the energy density of dark matter with the amplitude of these oscillations, absolutely. So then let me just tell you that there are two types of axion dark matter. They are hot and cold. Of course, axions have interactions, and then in the hot universe, in the hot Big Bang, some axions would be produced thermally. And this, as a function of the axion mass, the amount of axions produced thermally increases with the mass, because for larger masses, axions interact more strongly. So you have more axions, but at some point, the interactions are so strong that the axion decay is so important that axions cannot be dark matter anymore. And this happens around 10 milli-electron volt. And this helps me to remind you that axions are a very interesting dark matter candidate, because they have a coupling to the photons, and therefore they're always allowed to decay. So they are decaying dark matter, okay? However, this thermal dark matter would be hot dark matter, because we are talking about very small masses, right? And the temperature of the universe now is around this milli-electron volt. So hot dark matter is excluded from the point of view of large-scale structure. However, axions can be produced, or dark matter, axion dark matter can be produced non-thermally. One of the mechanisms that I've already told you about is this realignment mechanism. So the axion finding the minimum of its potential coming from a random value at the beginning of the universe, or at the beginning of phase transition. So, and but there are others, like, so in some scenarios, axions come with cosmic strings and domain walls, and so these also produce very cold dark matter, actually ultra cold dark matter. And yeah, so if you see, thermal dark matter can actually never make it to the dark matter density today. Okay, the average dark matter density today, which would be here around 1 kilo-electron volt per cubic centimeter on average in the universe, but non-thermal dark matter mechanisms can actually do. The only problem, well, they can do. The problem is that we cannot predict, because they are non-thermal, so they don't depend on the temperature, and they depend on initial conditions. So we cannot make a prediction of the axion mass that will give us all the dark matter density. In particular, if the dark matter is realized only by the realignment mechanism, and we have a period of inflation that made the initial value of the axion homogeneous in the whole universe, depending on this initial value, we can have axion dark matter for essentially any mass below a few milli-electron volt, below 1 milli-electron volt, okay? So there's maximum uncertainty. On the other hand, if inflation doesn't play a role, so then we can take an average of theta and include the contribution from strings, and then we have more or less a prediction around 100 microelectron volts or so for the dark matter mass of the axion. And yeah, and you see, well, here the effects of axion decay are going to be extremely small, but they are still non-zero, which is very interesting. And so before I go on, let me just tell you that, of course, the axion oscillation is going to be related to a frequency, and but I am expressing here the mass in milli-electron volts, so you might not be familiar with these units. And however, you might have in mind, as if you have some radio astronomers listening to a frequency, and so these mass scales where the axions could be oscillating, they are actually in the very interesting regions for radio astronomy. Gigahertz, in the gigahertz to terahertz range is the typical value where nothing has to be fine-tuned. Very good. So before continuing, let me just go very briefly through something that I've already told, that is axions are decaying dark matter. And therefore, one can, in principle, just search for monochromatic lines for dark matter-rich structures. So, and this has been done, and so far, no monochromatic line of significance has been observed in the visible, and there are even prospects for in the microwave range, okay, for SKA, that tell us that unfortunately, this SKA will not be very sensitive. Not even in dwarf spheroidal galaxies, which are dark matter rich and have very low background. So this is not very interesting, perhaps, in case you thought about this. But there are some other, but there's the stimulated decay, in which the axion does not decay into photons, but just borrow a photon from a magnetic field present in some source or in some background, and then it converts into a photon, like essentially in a helioscope experiment, but just for dark matter axions. And there was a very nice story in which Quinn and other people from the SKA collaboration, they put up a very strong, well, they showed that if axions in the galaxy could convert in the magnetic, with the typical magnetic field strength of the galactic magnetic fields, then SKA could actually detect axions. They would have enough sensitivity in the gigahertz frequency to detect QCD axions in this band. So because the sensitivity would reach the QCD band. However, Gunther Siegel showed that actually what is relevant is not the size of the magnetic fields, but the size of the Fourier component of the magnetic fields at the coherent or the typical Compton wavelength of the axion. And there, which is small, for a gigahertz would be of the order of centimeters or so. And therefore, and typically we don't have a lot of magnetic fields with a coherence length of centimeters. So then the sensitivity of SKA to this stimulated decay also decreases very much. However, very strong magnetic fields can be found in nearby compact sources like magnetars, right? And some people pointed out very recently that axions or dark matter axions could convert very efficiently in these atmospheres of magnetars, and the sensitivities are such that if you have a magnetar close to this galactic center where there's a lot of dark matter, and you are very lucky, you could actually have sensitivity to discover the QCD axion. But so this is the most hopeful forecast, but unfortunately, it is very complicated to model these such atmospheres, and there's a lot of work still to be done. So, Carlos, I think I'm already at 45 minutes. Is that true?
Yeah. So you were supposed to finish like in 9 minutes, but I don't know how. Do you have many slides left?
Oh, I think I can. You say 9 minutes? I think
till we meet the hour. We may extend it a bit beyond that.
Okay. No, I will finish. Okay. So I will be a little bit more light here in telling you how can we detect these axion oscillations or the oscillations of this axion field in the Earth in the laboratory. Okay. So first, just note that with the current density, dark matter density around us at the Earth corresponds to something like 1 GeV per cubic centimeter. And this tells us, or this informs us, that the amplitude of the oscillations of the axion field around us has to be of the order of 10 to the minus 19 to explain the dark matter. So these oscillations are super, super small compared with the sensitivity that we have to a constant value of theta. If you remember, we were able to exclude values of 10 to the minus 10 to the minus 10 or so. So it would appear that actually there's no experimental technique that we can use to detect oscillations of the axion field of the order of a body which is more than 1 billion times smaller. But actually there is, because now this amplitude is oscillating with the frequency, and therefore we can just couple this oscillation to some resonance detector. And so here in this slide, I just wanted to very briefly flash that there are very different techniques to try to convert the oscillation of the axion into some, so to make it resonant or resonate with some different device or in the laboratory to detect the axion dark matter. But I'm going to briefly discuss only the most relevant here for this audience, I hope, which are going to be essentially the cavities and mirrors. But please ask me about the rest if you're interested. I'll show you only the sensitivities at the end. So the fundamental principle that we are using to detect axion dark matter in the lab is very similar to the helioscope that I've already told you. So it's essentially going to use the fact that axions couple to 2 photons. And so if we put a very strong magnetic field in our laboratory, axions can convert into photons there. Okay. Another way to look at this is that if we have the axion coupling to photons in a magnetic field, so the axion coupling to photons is going to modify Maxwell's equations, which most of you know very well and are very familiar with. And so you see that there's a new term added in the right-hand side of the Maxwell equations that behaves or looks like a source, right? Like an electric current, which is proportional to the time derivative of theta, okay, and to the magnetic field. So if now we put a very strong magnetic field here, this is a constant. These are all constants. This is an axion constant of order 1. This is the fine structure constant. This is the magnetic field that you put, and this is dark matter oscillation that I showed you before. So then this current will produce you some electromagnetic fields that we can detect. In particular, if this B field is homogeneous and static, then you can read immediately that there's a solution of this equation. We just forget about this and forget about the source, and then the derivative of displacement current is proportional to the derivative of the theta field. So you will have an electric field which is proportional to the theta field, okay? So there will be and because this is homogeneous, the electric field will be homogeneous. In an homogeneous magnetic field, the axion dark matter field produces a constant electric field that oscillates, flipping sign, at a frequency given by the axion mass. This is the main effect that we are going to try to detect, okay? Now this gives us, so this first observation can be used in the following way to produce some observable photons. Imagine that we have a magnetized mirror. So we have here a mirror and a magnetic field. Now, this automatically induces an electric field, which is homogeneous here, but oscillating in time, right? But now there's a problem with this solution, and is that we know that the boundary conditions at the surface of a conductor, of a mirror, have to be that the electric field, which is parallel to the conductor, has to be 0. So then what happens is that the mirror is going to allow its electrons to move, right, to create a current, and this current is going to radiate to produce an electromagnetic wave, a normal regular electromagnetic wave caused by this source here, that is going to be essentially like if the axion induced field would be reflected by the mirror, okay? And now, so this axion induced electric field is going to produce photons from the mirror, okay? And the typical power that we can produce is something which is very weak, but not very scary. It's something like 10 to the minus 27 watt per meter for a magnetic field of 5 Tesla and so on. So the best idea so far to detect these photons is actually not to try to find these photons directly, but actually encapsulate encapsulate them in a resonant cavity. So build a resonant cavity inside a magnetic field, and try to tune the frequency of the emitted photons to one resonant mode of the cavity. Because in this case, if you just now put an antenna inside of the cavity, you can extract a power which is enhanced by the quality factor of the cavity. Because essentially, the Axion field oscillates and produces coherently a wave that increases linearly in time, and up to this quality factor of the cavity. So this is very nice. So you can integrate the power coherently. If, of course, if you hit the frequency that the resonant frequency that is given by the axial mass, which we don't know exactly, right? So then this means that because we want to have the quality factor as large as we can, to have the power as large as we can, then this means that this the response function is going to be quite narrowly picked around the resonant frequency, and therefore we can only search something like one axial mass at a time, and we have to slowly tune the cavity, so the resonant mode, to search if the axion is there, and if we don't find it, we just switch it again, and so on. So it's like trying to tune in to a radio channel whose frequency you don't know. And so you have here the world's most famous resonant cavity, that of the ADMX experiment. So so still the signal is super weak, and therefore the typical exit of the cavity is just dominated by thermal noise and amplifier noise, and even quantum noise is important. So one needs to do some to use the Decay technique to measure a narrow line on top of these backgrounds. And typically, in order to minimize the background, you need cryogenic. So you need to put the cavity in a cryogenic environment of sub-Kelvin temperatures, which is very similar to some of the radio techniques that you use in radio astronomy. And this technique is extremely powerful, and for masses around 10 to the minus 6, where cavities, where the typical lambda half cavity is of the order of 1 meter. But it is actually not so efficient, or it becomes more and more complicated as the axion mass becomes larger, because then the wavelength, the frequency grows, the wavelength becomes shorter, and the typical size of the cavity becomes smaller. So at some point, one can, so if we compare the emission from a disk to the cavity of a typical size, which is lambda halves, then at some point it is easier, or it might be easier for detecting the axion to just completely renounce to the quality factor and just increase the area of your emitter. And you can see that you can compensate very nicely a factor of 10 to the 4 if the area is such that area times mass squared is of the order of 10 to the 4. If you compare the emission of the dish antenna or of a mirror with the volume emission of the cavity. Nevertheless, there are some people that want to do this dish antenna experiment. It would be just simply magnetize a mirror and let it radiate, and then concentrate the photons in a detector. And we have here two very interesting experiments. The brass experiment that even will double this setup to just do to correlate both signals at the detector, and the bread experiment at Fermilab, that instead of using a magnetized surface, planning to use a solenoid, and then use a concentrator here, which is just essentially used to put all the photons that would be emitted radially into the tip of this cone. And so the sensitivities are not very good to reach the QCD Axion band, unfortunately, although you see that they are not very bad at high frequencies, so they scale much slower at high frequencies. But here I find something that I wanted to point out is that typical ways the typical way of detecting the photons in these experiments are just with Hempt amplifiers or quantum devices, JPAs or squids and so on. where which are quantum limited, or they have noise temperatures which are higher than the quantum limit. At some point at high frequencies, it is clearly better to use a bolometer, the photon counting device. And if you are able to perfect a quantum, a photon detector in these frequencies, we're talking about gigahertz to 100 gigahertz or so. Of course, at terahertz, there are many options available, but at low frequencies, not so much. So if one is able to have backgrounds of something like 1 millihertz in a low background detector, a photon counter at these frequencies, one could actually reach the QCD axion band. So it's really a matter of building the right bolometer that these experiments can actually improve substantially. So, and the final experiment that I wanted to tell you more in detail about was a mixture between the cavity concept and the dielectric, and the dish antenna, in which the idea is to try to keep the large increase of the power that can be produced by having a large area compared with the axion mass, okay, with the, let's say, with the Compton wavelength of the axion-induced electromagnetic waves. So you can keep a large area, but you can have some resonant production or some coherence. And the best idea we have come up with, I think at the moment, is this using not only one mirror, but using dielectric disks, because what we showed is that also in dielectric disks, from the surface of dielectric disks, axions would induce electromagnetic radiation. And since these dielectrics can also be semi-transparent, so then you can just they can be, so that the electromagnetic waves can move freely and be detected at the receiver. But what the detector would detect is just a combination of all the waves produced from in each of the layers after many reflections, of course. And since each of these layers can produce more or less the same amplitude, the signal can be boosted by a factor of n squared, because if you engineer the system cleverly, you can have the emission from all the layers add up coherently, right, in phase. So in principle, with a few layers, you can have a nice boost factor. That's why these dielectric helioscopes give you a power which can be enhanced with respect to the much larger, can be enhanced much more than a dish antenna. So at the end, this is a compromise solution between the typical cavity of lambda halves and the dish antenna, and it has some advantages from both and some disadvantages from both. Like, for instance, of course you have to put a lot of mobile elements, and you have to tune the distance from the disks in order to make them coherently, in order to make them add coherently the signal, and so this is a lot of technical development that is extremely challenging. And also another problem, well, not problem, but the fact that you are adding the signal coherently, it automatically means that the experiment is not broadband. So you really will need to scan as well as with the cavity experiment. However, you have an intermediate case in which the band doesn't have to be so broad. So you can have so that you don't need to scan in many steps, because each step is going to be quite complicated, and still have a large power because of the enhancement of area. Okay, and this is the best scheme that we have found, I think, at the moment for the region of 100 microelectron volt, which is very interesting for axion dark matter. There are like 3 experimental realizations or proposals along this direction. The most developed one, or the biggest experiment at the moment, is the MADMAX experiment that was proposed in 2017 already, and has been developed mainly by the MADMAX collaboration, which started at the Max Planck Institute, where I was. But now it will most likely take place in DC if we find the money to build the magnet, because we need a huge aperture dipole magnet. And we plan to have up to 80 sapphire disks of lanthanum aluminate or sapphire, something like this, coupled to so here you have the disks in the big mirror, and then there will be a parabolic mirror.
Oh, can you hear me? Sorry, we should speed up because we're running out of time. We're really exceeded the time. Do you have many slides, B?
No, we are done.
Okay.
A second experiment that I don't want to go before mentioning it was proposed by Javier de Miguel there in the Institute of Astrofísica de Canarias, and which is very similar in a sense to MatMax. It consists also on a magnetic field with electric disks, and instead of trying to exit the photons in one direction and collect them here, so the idea is that this magnet would be a solenoid, so that actually the photons would just move perpendicular to these surfaces, to these dielectric surfaces, and would exit against the walls of the magnet. And then instead of putting just one horn antenna, there would be many horn antennas detecting the photons, and these signals can be then combined and coherently or incoherently, depending on what you want to do with this experiment. Depending on what signal you are searching for. Oh. And there's a version in the Visible as well, proposed by Lassenbach et al. But I'm not sure whether they are actually doing this experiment or not. So just to conclude, visually, let me just show you this plot in which I show you the typical ranges. So this is the axion mass and decay constant, with the typical ranges where axion can be dark matter if we only rely on the realignment mechanism with one initial condition, which would be we would have all this range essentially, but there will be a non-fine-tuned region around 10⁻⁵ electron volt, and scenario B with cosmic strings and topological defects, where the typical mass ranges are 10⁻⁴ electron volts. And here I show you the best experiments and that can search for axions in the different ranges. I have not told you about Casper or the dark matter radio. This for next talk, but I discussed the cavity, which is the most mature axion dark matter experiment, the dielectric helioscopes, and the dish antennas. Okay, that could cover more or less the dark matter interested region, searching for in a clever way for this axion-induced electric field in a magnetic field. And I've also told you that YAXO can search for axions that would actually give you directly these astrophysical anomalies that could be of some interest. And as a word of warning, I just tell you that most of the experiments that I've listed here are actually in R&D phase, and the only mature techniques, the only experiments that can tomorrow be built and sure that they will work are actually the cavities and the YAXO, the helioscopes. Okay, so the rest we're still working on that. So my conclusions is I think they follow more or less the exposition of this talk. I think the strong symmetry problem can be a hint of a very new exciting particle, the axion. Axions would be producing the stars and would have effects. They would affect the stars. They might be already affecting some stars. And perhaps the best way of checking whether this is actually the case would be just to best detect them with the solar axions with direct detection experiments like YAXO. On the other hand, due to the mechanism by which the axions solve the strong symmetry problem, axion cold dark matter is completely inevitable, and this is very exciting. And actually, there are a large number of dark matter experiments that can be sensitive enough to search for axion dark matter with the particularities that I've been giving you across this talk. Let me just also conclude by saying that unfortunately, when it comes to the plethora of experiments that are available or that are being pursued, I've only scratched the surface. So if you want to know about more of them, please invite me again. And I'm very sorry for speaking a bit too much. Thank you thank you for your attention.
This has been a profound and deep review about actions. There's been a lot of information. Yeah, so we don't have much time for questions because we already exceeded the limit by 12 minutes, but there's already a few questions here. So let me go up to Jorge. Jorge, you can talk now.
Okay. Hi, Javi. Very nice talk. Thank you. I have basically two questions regarding these supercooling anomalies. You mentioned the white dwarf hints and so on. But if I remember correctly, also at the wake of Xenon 1T, the Xenon 1T signature, that it was attributed, that in principle, also to the possibility of solar axions. I remember there were a few analyses of the tip of the red giant branch, which made this supercooling anomaly quite unlikely. Do you know? Can you comment on that?
Yeah, I think yeah. So the tip of the the anomaly of the tip of red giant branch of M3 was always very weak. Mm-hmm. So actually, we did the analysis and we found something like 1 sigma discrepancy, and it was a general sigma. So we didn't believe it so much. So this was the weakest hint. And then very recently, I think last year, for instance, we had a very nice paper by Raffelt and Capuzzi, which I think reviewing everything a little bit better and updating also the distance measurements to M5. They showed that this was completely.
Also, there was a global analysis by Gianotti and collaborators. I think
exactly. Yeah.
20 global clusters, and then they basically. Yeah.
You're right. Yeah, exactly. So this is not significant. However, so there's still the significant. So if you put everything together, in principle, the white dwarf luminosity function hint is so strong that if you weight them equally, you would still have some hint.
But then, yeah. How would you explain the fact that you are not seeing anything anomalous on the tip of the red giant branch of many global clusters? I mean, is some stellar systematics, you think, or?
Oh no, that would be the errors are larger simply.
Okay.
So, yeah. So that would be my explanation. So okay. Really that it's not sensitive enough.
Okay.
Thank you, Jorge.
Very good point.
Chema Diego, you're there.
Hi. Thank you, Javier. Really nice talk. I learned a lot. In one of your last slides, maybe you saw this at the beginning. I missed the beginning. I'm sorry. You saw limits on the black hole superradiance, and from the plot, it appears like everything below 10⁻11 eV, it's excluded. But is that the case, or is only a narrow range in energies that is excluded by the superradiance?
Yeah. So I didn't mention this. So this is one of the astrophysical probes I had no time to comment on. So it's very nice that actually you allow me to speak about this. So this excluded region here is excluded from the fact that if axions at these masses would exist, so they would be spinning black holes would radiate their spin very efficiently by creating an axion cloud around them. So essentially, the black holes will transfer their spin into a spin of an axion cloud, and this happens exponentially fast. And so this means that black holes with a given set of masses would be very unlikely to observe with spin. Okay, because that would be a very efficient way of killing the spin or just dumping the spin of black holes. But black holes with those masses, masses in this corresponding to these axion masses, have been observed spinning. So therefore, axions in this mass range, they cannot exist. Otherwise, stellar black holes that we have observed would not have spin. Having this said, so this mechanism works very efficiently only if the Compton wavelength of the axion, which is the axion mass, is of the same size or very similar size to the Schwarzschild radius of the black hole, right? So actually, this argument applies only to axion masses that have the typical Compton wavelength similar to the Schwarzschild radius of stellar mass black holes. So this is an excluded band and not an upper limit. Okay. Yeah, because we don't. So essentially, we don't. If we had observed black holes with Schwarzschild radii much larger than those of a stellar black hole, we could have already excluded or found the axions at smaller masses. So there are actually two such bands. There's one at 10 to the minus, I think 17 electron volts, which corresponds to the Schwarzschild radius of the black holes at the centers of galaxies. But this is not so relevant for QSDD axions because for those QSDD axion to have such small mass, you need a decay constant which is higher than the Planck mass, and some people does not find this very appealing. So there are like two bands excluded.
Thanks.
Thank you, Javi. There's one more question at least, reading in the chat by Diego Blas. Not sure. Diego, can you talk? You want to ask the question yourself?
Yeah, of course. Hello, Javi. What's up?
I do.
Are you in Zaragoza?
Yeah, indeed.
Cool. Yeah, I'll see you in a week.
See you in a week. Yeah? I cannot show you Pilar from my office.
Fuck. Well, you can see the pillar from everywhere, I think. Anyways, something I'm now in the Institute of Astrophysics here with these guys, and yeah, we have some talks about possible fluxes of axions that may be at reach of these detectors. So, of course, the sun is a great flux, but is there any other astrophysical body that may generate something in the axion? Because normally what you do is the axion converts into photons, let's say, and then you detect the photons. But if you just want to detect the axions, what do you think? Is there any kind of couplings that can give us some
we did a study
notions or whatever?
Yeah. So we did a study of the flux of axions in natural sources, and so different astrophysical bodies producing axions, and then what would be a flux at the Earth. And I think I have, oh no, not here. I have a plot somewhere. Maybe I can show it to you. But the bottom line is that so the most abundant flux is that of dark matter axions, and then afterwards the sun is perhaps I think the most promising. But there are of course some others, and for instance you can have a nice flux of axions from dark radiation, and supernova. A nearby supernova would produce also a very interesting flux of axions in the gamma ray range. Sorry, it's not here. Where is it? Maybe here. No. Okay. Maybe. Well, I think a picture is worth more than 1,000 words, so it is really better if I show you this in my review. Oh yeah, here we made this this plot, and here you have the typical fluxes. Well, this is energy density more than flux, so you need to multiply again by a momentum, or divide by momentum. But here the dark matter is the absolutely most abundant, and this is one example. Dark radiation is not that bad. And these were the absolute upper limit that we could find. So it can be smaller, but not higher than this. And dark radiation, these two types of dark radiation. The sun, and this is the diffuse supernova axion background is not very high. But so if Betelgeuse explodes tomorrow, the flux at Earth would be, of course, much higher, and it would be that size. So yeah, and the rest of the stars I think they were much less interesting than the sun. So in particular, yeah. So when we talk about
which kind of couplings do you use for this? Like,
yeah, here you have the photon coupling. So this is this black line, and the electron coupling, and the fluxes are the maximum, which are allowed by
the
astrophysical limits.
Thank you. That's very interesting.
Thank you, Javi. Thank you, Diego, for the question. I think we hit a record today in terms of extension of the seminar, but I think it was very interesting. It was great having questions at the end. Yeah, so let me check. Yeah, there are no questions in the YouTube channel. So I think we're pretty much done for today. So thank you everyone for attending. Thank you, Javi, again for
It was a pleasure. My apologies for over speaking again.
No. Actually, as you said, it's a nice excuse. We hope to be able to bring you here when the lockdown is over, when this pandemic is over, so you can come here in person and talk to the people here.